I am Bálint Daróczy. I'm from Institute for Computer Science and Control, and I would like to show you. It's a bit a trickier part of. It's connected to machine learning. We try to utilize one of the most important parts of physics, obviously the Riemannian metrics, and try to understand what are the connections between the machine learning models we use usually and the data we observe usually. So let's start with some kind of motivation. And the first motivation is coming from a real simple experiment. Just imagine that we have a neural network. We heard a lot about it today and yesterday. So just imagine that we have an input. For simplicity, we will think that it's a simple one-dimensional data, and we somehow trying to push it to the right from the left. So it's a simple feed-forward network. Every single step, we transform the data with some kind of very simple linear transformation. After that, we apply an activation function, which is usually not linear. But we have some kind of parameters, free parameters, which are obviously our goal to determine if we are training a model. So what you can see here is after some iterations, we stop the network and try to ask for, based on the output, which here is obviously 10 outputs, that what are the most important weights in the neural network, free parameters, per layer for that question, on average, on our test data. What we can see that it's very different per categories. So here the data was originally the MNIST data, which has 10 categories, and these 10 networks which were put together into a picture are the 10 different subnetworks, network connections per category. So the black ones are the important edges. And here you can see clearly that we can see that they are really distinguishable. So based on what you wanna have as an output category, you can determine what was your data in a way. Obviously, we know what are the original labels. So what we know outside of this, we know that these feed-forward networks are really a strange thing. They are hierarchical. They are directed acyclic graphs. They are usually continuously differentiable across the board. Of course, ReLU is not at every point differentiable, but we think of that like that. And it's trainable via backpropagation and so on. We even know from recent results that for some type of problems, usually the local minimums are close to the global ones. That's an empirical result, obviously, so no theory behind it. And if we are trying to understand what are the connections between the free parameters in our space, there will be some kind of connections. We will know that the neighboring layers parameters are connected in a way. Usually the weights, the free parameters inside the layer are not, or not as much. And obviously the far away free parameters are not so well connected in a way. So how can we utilize this? The other motivation is coming from recent results from Tegmark and such. They are trying to understand why deep structures are much better for learning such things like images, and their result was really interesting in a way. The first thing which caught my eyes was that they say that the Hamiltonians at every layer are less than 5-degree polynomials. The other one is that they introduced the network gates for making polynomial networks. Nobody implemented it yet, but that would be really cool to have. So not just like now. Nowadays, we are trying to approximate polynomials via a lot of strange structures, but not obviously making multiplication. And the third one is coming from a bit different field, but not different in a way because that's machine learning. So we had two projects. The first one was with Ericsson. We tried to understand why the data connection is dropping between a cell tower and a mobile phone. And it turned out that all the models which was in the literature were just overfitting per towers. And we gave a model which turned out to be more generalized, and it was based on Riemannian metrics over random fields. And recently, it will be appear soon, we have a paper about conditional Fisher information, which is a Riemannian metric over normalized, for normalization of the gradient embeddings for recommendation systems. So obviously, if we can know something about this gradient structure, it may help us to understand what's going on, why the network trains, which part of the network is important. So how to do that? First, we have to understand what we want to seek and understand. So there are three surfaces or type of manifolds which we could define in machine learning. The first one is the data. Usually we didn't know anything about it. We know some kind of sample, but we cannot assume anything. It could be anything, right? So we don't know what is the point, the data. The second one is usually if we are making a hypothesis over the data or our problem, we can make a loss surface, usually, which contains differentiable functions. And the third one is very tricky and really interesting, is a hyperparameter surface. So what are these? This is a typical, this is the loss. And what you can see there is just a simple two-dimensional linear separator over these data, the color indicating the target. And what we can see, it should be smooth, right? It looks smooth. And obviously it's smooth. So if we can describe it, maybe we can utilize it. How? Maybe if we are in the 4, we can be much faster to reach the bottom, right? That's the old momentum and all the other methods are utilizing. So this is a typical differentiable manifold. The trick is that it doesn't depend on the data. Data are just samples, which are usually finite, but the loss surface could be continuous and differentiable, even if the data is not, or we don't know anything about it. Why? Because our hypothesis should be differentiable and continuous and not the data. And usually the data is not because it's finite. So what are the manifolds? And why is it important to understand what are they? Usually the manifolds are really a simple structure. You can see that it's objects with n degree of freedom. What does it mean? How many parameters do I need to parameterize all the points on the surface, like a surface there? So if it's a solid ball, we need 3 parameters. If just the surface of the ball, we need only 2, right? Because we can map it into an atlas. So what kind of manifolds we want to seek? We would like to have some kind of topological manifold. Why? Because they are resembling Euclidean homomorphic to Euclidean, which is a good thing to have. It would be nice to have a differentiable manifold. Why? Because if the manifold is differentiable, that means that the transition from point to point on the surface is smooth. So it's like I'm going from this point on the Earth and going a bit away, the transition will be smooth, which is nice to have. And one of the differentiable manifolds we want to use today is the Riemannian manifolds, which even have other properties, like they are having inner product subspaces at every point on the surface. That means that we can calculate inner products. And we will utilize that. We will use that. And these inner products are depending smoothly on the surface. So that means that the inner product will be a smooth transition between points to point. So, what kind of manifolds are our data, usually, or our problem? Usually the data is not topological manifold, we cannot assume anything about it, so don't care about it right now. The second one is the loss. Usually it's a differentiable manifold. If it's a neural network with typical activation functions as typical structures, they are. I highly suggest the first paper because it's a really large paper, 50 pages long, and it's really dense, but it's a very cool paper to understand what's the connection between the two. I tried to find a proper paper about it for years, and in 2015 I found that. So I was really happy about it. And there is a well-known sub-manifold set, which is the statistical manifolds, which based on the log likelihood surface. And it's well-known, and it has a really cool properties, which we cannot utilize on the neural networks, only if we make some tricks. But the problem is, these statistical manifold surfaces are not regularized manifolds. So the main problem is that we know a lot about the log likelihood surface, but we don't know anything about if we have some regularization in the parameters. And the third one is the trickiest one, because we don't know anything about it, even we cannot approximate it well. Maybe you heard about these kind of three things which we care about when we are trying to train neural networks. The first one is the network structure, how we make the graph, right? The second one is the regularization, dropout, and all the other tricks to maintain it, not to overfit. And the third one is a very important one, but rarely spoke about it, augmentation, which means that obviously if I take a picture, I can make the same picture right here. The content will be almost the same, right? So I shouldn't say anything completely opposite about the two pictures. So where do they belong? Augmentation belongs to the data. We are usually making augmentation before we do anything with the data. So that's just a trick to make our data dense, more dense. Obviously, if we have all the data, then we don't need to, because augmentation will be there naturally. Regularization and dropout, it's on the differentiable manifold part. And the network structure, which is the trickiest, because we don't want to experiment with all the structures, is on the hyperparameter surface. So like the hyperparameter surface could be that how deep is our network and so on. But there are really cool papers about it recently, so even with Fisher information. But let's keep to the metric based on the loss, because that's what I can show you what we could do. So the simplest solution how to find paths on the surface, if we know that it's a smooth surface, is that we use simple first-order gradient descent, right? We start from a point, and in small steps, we try to reach a local minimum. We do that every day. Obviously, we are stuck at some point. That's why we need dropout, that's why we need regularization, and all the other tricks. We could even make it faster with momentum. So it's from Polyak 1964 that if our ball started to have a momentum, we let it. And momentum is a tricky one because maybe we could jump out of the local minimum because of the momentum, but there are other tricks and a lot of things which we try to use, like adaptive gradients, where we are trying to understand which part of the parameter space was not used enough, and so on, so on, so on. And there are some which we know theoretically are at the border, like the Nestor one. The other way is to try to make the exponential map. So that means that we are trying to move on the surface, but when we move, we are not moving exactly as the surface, we have to map it. And that's a tricky part, because you will see that exponential mapping and all the other tricks are not sustainable right now because of the high number of parameters. So the one is that we try to approximate proper metrics, which we know a lot, like Fisher information. The other trick is that we try to learn the metric, and what that we will be doing today, in a way. Of course, that will be not the best metric in a way, just usable. So what kind of predetermined metric can we use? So like Hessian metric, which is more like an extension of the Fisher one. We can use the second order gradients, obviously. And there are some really interesting and promising results from Wensing and Schra. Geodesic convexity, which means that we don't have convexity, but we have geodesic convexity. So that's a bit releasing the non-convexity of the surface. And they are really promising. So I think they will help a lot in the longer run. And we were thinking about that, yeah, obviously the Hessian or the Fisher are ideal for a lot of things. Why? Because the second order gradient can be used to normalize the gradients to optimally going where we should want to go. But how? So what will be the metric? So the metric will be that we have a quasi-arithmetic mean over the Hessian, where we are stopping at points where it satisfies the Mersenne conditions. It's very important because a Hessian is not positive definite every point. We need to have a positive definite metric. Obviously, we can skip it like pseudo-Riemannian metrics, but it would be easier to stop at some points where we know. And we can approximate it via dot products. So that's what we are doing. But it has to be on the GPU. And here comes the most trickier part in a way, after we say that we want to do that. But what we want to do? So let's start with some kind of dimensional analysis. So let's be n, the number of free parameters of the underlying model. That's a neural network. So the ResNet 50, which is the small one. So just imagine this is the small one, has 25 million parameters. And the dimension of the gradient will be 25 million parameters, 25 million. The Hessian will be on the square. So that means that we can even fit on a typical machine. So that's not even approximating it. We cannot even calculate it and store it. So what we know about this gradient? The gradients are layer by layer, concatenated into one vector in a way. Yeah, we can say that. And obviously, these could be handled as tensors, and they are not flat originally. So we can say the partial derivatives are leaving the structure. So our goal is to have the inverse of this metric and the square. Okay, we can do that, but we need to make this normalized gradient vector in a way. How to do that? Computational complexity is even considered too. So the first one is that because of the expectation in the age over the mean, it's not suitable, but there are some tricks for that. So we can do that, the approximation via a validation set. And of course, the inverse computation is usually in the literature is handled by diagonal approximation for other type of problems, so not for this. But you can do that. But what we know about this structure of the parameters? The interesting property is that if our model is reaching its some kind of bound, usually it will be sparse, very sparse. Why? Because you don't want to change the parameters via sample, so it will be very sparse on average, but not on individual ones, so it's a bit different. And in this case, we can say that there will be surviving paths. So the idea was that, yeah, do that. So we started with some simple, we can start with simple 3-layer neural network. So the first layer, second, third one. This is the gradient vector per sample. We can separate the layer. And after that, we just percentile rank, sparsify based on the percentile rank. So we leave only 15% of the gradient values based on their rank, based on their absolute value. So that means that we just keep the most important directions, okay? Why 15%? Because it worked best. But obviously, it could be more or less based on the original structure. But that's a good start, because after that, we have a sparse vector representation. Based on the sparse vector representation, we can say, and based on the structure of the network, and if you write down the Hessian of it, you will see that it's very blocky. So originally it's very blocky, but we know that this transformation would, can be a low rank approximation. So that means that we will transform this part with a small rank, small block. So at the end, we will have layer times factor normalization, which is much smaller than the 400 terabytes. Okay, the last problem we should solve is that the gradient representation has a problem because we don't know the original target. So the loss will be based on what? On a test sample, on a validation sample? We cannot assume that we know the target. And the interesting part is that based on the target, the gradients are very different. So the best solution was the mean so far, but obviously that needs improving. So let's see what we could achieve. And the interesting part is that what I was thinking before we started experimenting, so it's just imagine that it's a very small network with 120,000 parameters, so it's a very small network. It's on the CIFAR-10, and this is the best we could achieve with the Bayes model, Bayes network. So it's a very small one. And based on the gradient, we could achieve it even if the network was not saturated. And we could achieve more performance. It was on the NIST too, and the interesting part, when we can approximate properly the metric on a small network based on restricted Boltzmann machines, you can see that nothing's changed because that is an invariant property. So that would be the goal on the large networks. And so just for the conclusions, the GPU memory can be a real constraint for really simple problems. So it's a very small network. We wanted to just understand what's going on in the gradient graph. And it turned out that it's a bottleneck. But what is a really promising thing that the accuracy was much higher if we sparsify the vectors. So in a way, we could say that because of the constraint, we had to make a workaround, and this workaround proved to be viable. Of course, it's more like denoising. So what I think, longer run, that I think differential geometry should and will play an important role in machine learning. And there are some really interesting new results about it, but it's far away from there. So we don't know how to really utilize this restructure of differential geometry. We don't know what's going on with non-Riemannian geometries. We don't know even how to pertain and utilize Riemannian geometry. And what will be the ultimate goal is to make, using all the things we know from differential geometry, to make non-trivial network structures, because we know that they are homomorphic. So that will be the final goal. And of course, maybe we can understand with Lie groups the other structures and how these models are connected and why they work. My assumption is that the underlying group has elements which are much more simple than the ones we use nowadays. Thank you very much.
Question time. Here and there. Okay, so let me get this right, if we can formulate the message clearly. If we use the Hessian to regulate or to normalize our gradients, to have better gradients inside our network, we can have a more robust guideline for the optimizer to reach into minima, right?
In a way, yes, but the main goal was to understand why it will be achieving the same result as the final model way before. Mm-hmm. So maybe the gradient structure is much more rich and much more invariant to a lot of transformations than we think.
By structure, you mean which components of the gradient are the most important?
And how they structured. Yeah, and how they structured together.
Okay, and what was raising in my mind is that usually when we have some sparse matrix problem, we try to have some decomposition of the matrix, some eigenvalue, projector decomposition, something like that. How this would relate to this kind of approach? Do they have something in common or not?
Yeah, of course they have. So the low rank approximation should be well connected to it. To maintain it and make it on the run, one of my students is working on it, but it's tricky to do because of the size. So everything should be really carefully. So these kind of things are for training just one iteration, and it's really fast to converge. So after one epoch, it's converged. So it's a really fast one. But it took, I don't know, on a Titan, on a Pascal, no, Maxwell Titan, I guess, half a day. So on a small network. So it's a large computational problem.
But GPUs are getting more and more powerful. So
yeah.
Hopefully in the future it will be much faster. Okay. Let's thank the speaker again for the great talk.